Have you been missing a lot of titration test questions? Well, no worries. I'm going to explain titration simpler than you thought it could be to help you get these questions correct every time. Since acids and bases tend to only dissolve to their equilibrium or buffer point in most natural conditions, which is when only half the acid or base is dissolved, titration, a technique that fully dissolves acid or base samples, is used to investigate their properties. The titrand is the unknown acid or base sample, and the titrant is the known base or acid used to measure the titrand. A titrant is used to titrate a titrand, or more simply said, a titrant is used to titrate a sample. And because acids are more soluble with bases and vice versa, acids are used to titrate bases, and bases are used to titrate acids. I don't think I've said titrate enough times, so let's get to it. Here's the titration curve that you're very likely already familiar with. I'm going to show you what happens when titrating a monoprotic acid where hydrogen, upon dissociation, is the acid itself, and the titrant base contains a hydroxide, which upon dissociation is the actual base used to titrate the acid. And we'll watch the changes in pH on the y-axis while adding base titrant along the x-axis, and talk about the significance of certain points along the curve. Let's watch exactly what happens in a beaker where we drop two protonated acid compounds in. Before titrant base is added, half of the acid sample dissociates, meaning naturally dissolves in solvent, and due to the hydrogen becoming a proton, a positively charged hydrogen ion, which is the acid itself, notice on the y-axis that the pH starts off very low, meaning very acidic. This is because the solution is saturated with protons, which are acidic. Then, after adding a precise amount of base titrant, in this example, one base compound, the hydroxide base readily reacts with the proton, neutralizing it into water. Notice that the pH increased only a little on the y-axis when we reached half equivalence point, which is when half the acid in the beaker was neutralized into water, recalling that we started with two acid compounds and now only have one left. And this is why half equivalence point may also be referred to as half neutralization point. Before I talk about half equivalence point, I want to address a common question about why pH only increases a little on the y-axis after neutralizing half the acid. It's because as the first acidic proton was gradually neutralized into water, the solution gradually became less saturated with protons, allowing the second acidic compound to dissolve and resaturate the solution with acidic protons, keeping the pH low. But at the same time, since there's more water in the beaker now, the pH is greater than what it was before titration started, meaning before any neutralization occurred. Now back to half equivalence point. Since half of the acid in the beaker has been neutralized into water, this is when the concentration of acid compound left in the beaker, even though it's aqueous, meaning dissolved into ions in water, equals the concentration of newly formed conjugate base, creating an acid conjugate base equilibrium. So given the Henderson-Hasselbalch equation, if the concentrations of conjugate base and acid compound are equivalent, resulting in a log of 1, and a log of 1 is 0, we're left with pH equals pKa at half equivalence point. This shows that the pKa of an acid is the pH at which the acid compound is deprotonated until its equilibrium with its conjugate base, which is also known as the buffer region. A buffer is an equilibrium between the acid and its conjugate base, and because the two concentrations are equal to each other, there is no shifting left or right in the acid-base reaction, and because of this, a buffer strongly resists pH changes, which is indicated by the nearly zero slope at half equivalence point. Half equivalence point is important to know because pKa is the actual pH of the acid that would be reported on the pH scale. It's the pH that the acid would create in natural conditions. For this example, pKa is between 2 and 3, which means the pH of HCl is between 2 and 3. Since the acid conjugate base buffer is strongly resistant to pH change, more titrant base must be added to force full dissociation of the acid sample remaining in the beaker until it reaches its equivalence point. The equivalence point is when the rest of the acid sample in the beaker has been neutralized into water by the additional base added, meaning it's where all the acid has been neutralized and the solution now only contains salt at net zero charge, so it's also known as the full neutralization point. Notice the significant increase in pH this time, up to 7 upon deprotonating the rest of the acid. Since pH of 7 is neutral, this confirms that equivalence point is when the acid sample has been fully dissociated and fully neutralized. Equivalence point is also important to know because this is when we can calculate acid sample concentration that was initially in the beaker, because this is when it equals the precise known concentration of base titrant that was added. It's when there's an equivalence between the acid sample that was initially in the beaker and base titrant that has been added thus far. This equivalence is not technically an equilibrium like at half equivalence point, even though sometimes it's referred to as one, because neither the acid nor the base actually exist in the beaker anymore to actually be in equilibrium with each other. Here, it's an equivalence. It's when an exact amount of base titrant has been added to neutralize the entire acid sample to a pH of approximately 7, literally meaning mole for mole. And that's why it's when we can calculate the acid sample concentration using the base titrant concentration. So equivalence point is different than half equivalence point because the equilibrium back at half equivalence point was an actual equilibrium between the acid and its conjugate base that both existed in the beaker. Even though the acid sample was of unknown concentration before we started titration, for the sake of easily visualizing equivalence point, recall that we started with 2 acids in the beaker and added 2 bases to completely neutralize the acid sample. Equivalence point is when we can use MV equals MV, which is molarity times volume of acid is equal to molarity times volume of titrant base, whereby molarity is simply concentration. So we can calculate the concentration of the acid sample, knowing the concentration and volume of the base titrant that was added, and the volume of the acid initially in the beaker. And in the example that you've been watching, the concentration of the acid sample would come out to be 2, equivalent to the 2 acid compounds initially added to the beaker. Finally, even though all the acid has been neutralized, more base titrant is added to ensure titration of the acid is complete. And since there's no more acid to neutralize, the base just saturates the solution, increasing the pH significantly, reaching the endpoint, leaving us with a basic solution. So let's see what we can gather from our titration curve. Since half equivalence point, where we measured pKa, is low on the pH scale, it can be concluded that the acid sample is a strong acid, and this is the pH it creates in most natural/neutral conditions. Since titration ended at a high pH, it can be concluded that the titrant base is a strong base. And since the equivalence point is just about at pH of 7, meaning neutral, we can conclude that the acid and base are pretty equivalent in strength because strong acid plus strong base will equilibrate to a neutral pH. As a side note, to determine the endpoint of titration, you would want to use an acid-base indicator that includes the pH of the equivalence point, since that's when the acid sample was technically fully titrated. Simple as that.